All right, so today we are going to be talking about something that you have already seen at many stages of your studies, matrices. Okay. Okay. So the question is, why do you want to study about matrices in a quantum mechanics course? I'll hope to make this answer to this question clear as we go along. Uh, Basically, the one-line answer to that question is there is a very important notion of operators in quantum mechanics, and operators can be represented as matrices. So it is very important that we study about matrices, and in particular, there is one kind of matrix that we are particularly interested in, and those are Hermitian matrices. More generally, Hermitian operators. Okay, because operators don't necessarily have to have a matrix form. Uh, so we will talk about the concept of differential operators when we talk about function space. So, but it's very easy to discuss the important aspects and the properties of operators when one talks about matrices. So that's where we'll get started. So as usual, if you have any trouble hearing me, please just type it in the chat section. If you have trouble seeing what I'm writing, also type it in the chat section. Okay, so what is the connection between matrices and linear vector spaces? Well, I've already told you a couple of connections. Matrices can also be thought of as vectors in some vector spaces. The second connection is that matrices are operators in a linear vector space. This is basically going to be, old wine in a new bottle kind of discussion, at least initially. I want to stress upon you the important notion that the components of a matrix are very specific to the basis that you have chosen. Okay. Now, in some sense, this should not be surprising because we've already talked about vectors where I've written a vector, let us say U, in a column vector form, right? So the X component of one component, two component, and three component, and this, after all, is a matrix, right? This is a matrix with a single column and three rows. Now, obviously, the components of this vector depend upon the choice of basis vectors, as we have discussed both in class and in yesterday's tutorial problem. But what is not usually appreciated is that the same is true for any matrix, not just a column matrix of the kind a vector is. Okay. So, for example, if you take any rectangular matrix, let us say I don't know, some components, 2, 3, 4, and 7. Okay. The components of A are the 1, 1 component. I can write this as A11, A12, A21, A22. I'll take a simple 2 by 2 matrix to give you an example. So the A11 component of this matrix is 2, the A12 component is 3, the A21 component is 4, and A22 component is 7. So the claim is that the fact that the A11 is 2 is because you have chosen the basis to be something. So whenever I don't say anything, I mean that I've chosen the usual Cartesian basis coordinates. So again, the Cartesian basis coordinates I can write in terms of ij. Okay, when I'm writing vectors in usual symbols, this is the most convenient. But I can also write this in abstract bracket notation as some two basis vectors, two basis kets. So I'll call the kets, say 1 and 2. Okay, or I can equally well represent them as column vectors 1, 0, 0, 1. 1, 0 is the basis vector along the direction 1, or equivalently the x direction or I cap, and 0, 1 is the column vector that is the basis vector along direction 2, or equivalently in the usual notation j cap. Okay. So I'll mostly use the second and the third notations. I'll quickly move away from IJK notation because that is very specific to 3 axes X, Y, Z. But the second symbolism is very useful because it can serve to generalize it to arbitrary number of dimensions. The third symbolism is useful when I'm talking about matrices. So at least for today's lecture, I will both use notation 2 and notation 3 to represent the matrices, to represent the basis vectors. Okay. So the assertion is that the components of the matrix of this matrix A, which is 2, 3, 4, 7, are really 2, 3, 4, 7 only because I've chosen this as the basis vectors. Now, just like I can project out the components of U using the basis vectors, I can also project out the components of A using the basis vectors. So let us quickly recap how you do it for the vector. So suppose if I have some vector alpha, right? Now I can write this vector as a sum over the basis vectors. Now, if I want the component of alpha along some direction, let us say Ej, then I simply take the inner product Ej alpha like this, right? When I take the inner product Ej alpha, what happens? This becomes Ai, Ej, Ei, but assuming my basis vectors are properly orthonormal, the inner product of two basis vectors Ej, Ei is simply delta Ji. So this simply spits out the component Aj because the sum is only non-zero for j equal to I. So out of this in lots of different terms, I only get one term, the term for which I equal to j. Okay, so this is the component of alpha along the direction j hat. Okay, that should be obvious by looking at the equation prior to this. Alpha is sum over Ai, Ei. So this is how you project out the components of a vector. Now, how do you project out the components of a matrix, 2 by 2 matrix, let us say, or a 3 by 3 or a 4 by 4, whatever it is. We'll mostly be dealing with rectangular matrices. So let us take this example, A, 2, 3, 4, 7. Let me take notation 3, okay, and then I will use notation 3 to make basis vectors and tell you how the projection is done, and then I will write it in the more abstract form using representation 2. Okay, all right. So what is the 1, 1 component of this matrix A? So this is the question that we want to understand. What is the 1, 1, not 11, so I should say 1, 1 component of A? Now you will obviously tell me that's a silly question to ask because you can simply read it out. It is 2, that is fine. But I want, just like you can always read out the components of a vector, you can always read out the components of a matrix, but I want to get a formal way of deducting this, just like we got a formal way of deducting the components of a vector. The way I will get the component is as follows. Remember that if I want to get the components of a vector, I can simply multiply the vector by a bra because component is a number. And if I have a vector and I want to get a number, I can simply multiply it by the bra of that vector. I think on place of Aj, it is Ai. That is a question. No, this is actually Aj because look at the left-hand side. The left-hand side is, I am projecting out the jth component of alpha. Okay. So I need to get the jth component out. So the indices have to match on both sides. I hope that answers the question. Okay. Now, what is the 1, 1 component of A? Well, in the case of a matrix, it is not enough if I simply multiply it by a bra, because if I multiply it by a bra vector, I will simply get another matrix. It is not enough if I simply multiply it by a ket on the right-hand side of the matrix, because a 2 by 2 matrix times a column vector is another column vector. So either of these two operations does not give me a number. What gives me a number is if I multiply it by the row vector on the left-hand side and the column vector on the right-hand side. I should sandwich A between the two components I want. Suppose if I want the 1, 1 component, I should sandwich A between the bra vector 1 on the left-hand side and the bra vector 1 on the right-hand side. In the row vector column vector notation, the way I will get A11 is I multiplied by the bra, which is the row vector 1. What is the row vector 1? It is 1, 0. And then I multiplied by the matrix. My matrix is 2, 3, 4, 7. And then I multiply it by the corresponding column vector on the right, which is, again, since I want 1, 1, I should multiply it by the column vector corresponding to direction 1, which is again 1, 0. What is this guy? Let us actually multiply it out and check if we are doing something right or something wrong. This is 2 times 1 plus 3 times 0, which is 2. This is 4 times 1 plus 7 times 0, which is 4. And this is 2. And as you can see, the 1, 1 component of A is 2. Okay. So what is the 1, 2 component? I should multiply it by the row vector corresponding to direction 1 on the left, which is 1, 0 times the matrix. And I should multiply it by the column vector corresponding to direction 2 on the right. The column vector corresponding to direction 2 is 0, 1. Okay. Again, let us do this out completely just to satisfy ourselves. This is 2 times 0 plus 3 times 1. This is 4 times 0 plus 7 times 1. And this obviously is just 3. So the 1, 2 component is 3. Okay. Similarly, we can satisfy ourselves that the 2, 1 component is, take the matrix 2, 3, 4, 7. This is 2, 1. So I should put the row vector corresponding to direction 2 on the left, which is 0, 1. And the column vector corresponding to direction 1 on the right, which is 1, 0. So this is 0, 1 times 2, 4, which is 4. And A21 is 4. Now I'll complete this just to drive home the point. 2, 2 is, I should sandwich the matrix 2, 3, 4, 7 between the row vector corresponding to direction 2 on the left and the column vector corresponding to direction 2 on the right, which is 0, 1 times, this is 3, this is 7, and this is 7. Okay, which is the 2, 2 component of this matrix. So if I want to project out the components of a matrix, each component of a matrix is given by 2 indices, not just one index, right? The 1, 1 component, the 1, 2 component, the 2, 1 component, and the 2, 2 component. So the way you project it out, write out the components of a matrix is by multiplying it by the row vector corresponding to the first component on the left and the column vector corresponding to the second component on the right. There is a cleaner way of representing this using the Dirac bracket notation. Remember that whenever I say row vector, you should think of brass, and whenever I say column vector, you should think of kits. Those are not the only rows and columns, but that is those are not the only kits and brass, but those are convenient examples. So if I want the ij component of any matrix A, then I would take the matrix A and sandwich it between the EI bra and the EJ kit. Okay, this is the entire point. So the components of a matrix do depend on the basis vectors that are chosen. So if I transform to a different basis vector, my matrix is going to look completely different, as we are going to just demonstrate. So this 2 by 2 matrix, I can write, even though I don't want to write it this way, I can write it as follows: 1, A1, 1, A2, 2, A1, 2, A2. Okay. So pay attention to this A in the middle in all these expressions. This A would be the components of an operator in quantum mechanics, as we will discuss shortly. So I hope you're all convinced that the components of a matrix can also be projected out, just like the components of a vector are projected out. But the rules for the projection is slightly different. You have to, the components of a matrix can be represented as the matrix sandwiched between the corresponding column, corresponding basis vectors on the left and the right. In the Dirac bracket notation, it is the green box that I have written. Okay, those are the components of a matrix. So what happens to this matrix, for example, if I change my basis vector? So let us say that I go from change of basis. So I go from this set 1, 0, 0, 1 to a different set. Let us say 1 over root 2 times 1, 1. This is the example that we have taken in the initial lecture. Okay, 1 over root 2, 1 minus 1. So you can satisfy yourself. The second choice is also a proper orthonormal set of basis vectors for this two-dimensional linear vector space. It is two-dimensional because I need two basis vectors to understand it. All right. So how are my components going to be different? I'm going to do this calculation in the Dirac bracket notation because I want you to be comfortable with that instead of the multiplying it with rows and columns. So please follow carefully, and if there is any questions, please unmute your microphones and ask or type it in the chat section immediately, because this is something you have to be comfortable with. Okay, so written in the first basis, the 1, 1 component. So I will call this basis 1 and 2. Okay, and I will call this basis E1 and E2. I know the components of the matrix in the 1, 2 basis. I want the components of the base matrix in the E1, E2 basis. Okay, so let me try and work this out. So let me write this everything in the Dirac bracket notation. How would I write it? Well, remember that I'm going from 1, 0, 0, 1 to 1 over root 2, 1, 1, 1 over root 2, 1 minus 1. So my E1 can be written this vector. When I say E1, I mean this vector. You can easily see can be written as 1 over root 2 times 1 plus 2. And similarly, E2 can be written as 1 over root 2 times 1 minus 2. Again, if there is any questions, stop me. Why can I write it like this? Well, the vector 1 is 1, 0. Vector 2 is 0, 1. So if I add vector 1 and vector 2, I get a column vector with 1 on the top and 1 on the bottom. Okay, if I multiply it by 1 over root 2, I precisely get this vector. Similarly for E2. Okay, so I hope this should be clear. And yeah, I hope this should be clear. Now, these are all real vectors. So if I take the corresponding bra vectors, it should be equal to 1 in of course, in component notation, this is always true. Okay. But remember that if you are not dealing with real vectors, okay, suppose if I write a vector alpha as, let us say, 1 and 2 plus I, the corresponding bra vector is not the row 1, 2 plus I, but it is 1, 2 minus I. Okay. So the bra vector is the ket vector transposed and complex conjugated, both. Okay, not just transposed, it should be transposed and complex conjugated. But of course, all these are real vectors, so that complication doesn't arise in our simple example. Okay. E1, E2 are not normalized. Why do you say that? So let us check. What is E1, E2? Okay. So remember, my E1 is 1 over root 2, 1, 1. Okay. So what is E1, E1? This is equal to 1 over root 2, 1, 1. That is the bra times 1 over root 2. Oops. That is the ket. So this is equal to 1 half 1, 1 times 1, 1, which is equal to 1 half times 2, which is 1. Okay. So the length of E1 is 1. Similarly, the length of E2 you can also prove to be equal to 1. They're also orthogonal because E1, E2 would be 1/2 times 1, 1, 1 minus 1. So this will be 1/2. This is 1 minus 1, which is 0. Okay. All right. Thank you. So I will erase this part. Okay. Let us go back to this example. So now I want to write the components of A in the E1, E2 basis. So how will I do that? So I want things of the form. What is the 1, 1 component of A in the E1, E2 basis? It is, so let us ask, what is E1, A, E1? Okay, or what is E1, A, E2, and so on and so forth. Let us work this out carefully. So I will use this set of equations and this set of equations. They're the same equations for the kets and the bras. So E1, A, E1 is the bra E1 times A times the ket E1, right? But the bra E1 can be written as a linear combination of 1 and 2. So what is this equal to? This is 1 over root 2 times 1 plus 2 A, and the ket E1 is again 1 over root 2, 1 plus 2. Okay. So this is my bra E1, this is my ket E1, and my A remains as such. So let me multiply term by term. This is, there is a 1 over root 2 here, 1 over root 2 here, which becomes 1/2. Okay, times, there are 4 terms here. This multiplied A multiplied the first one, then 1 multiplying A multiplying the second, then 2 multiplying A multiplying 1, and 2 multiplying A multiplying 2. So there is 4 terms here, which is 1 A 1 plus 1 A 2 plus 2 A 1 plus 2 A 2. Now, please stop me if this step is not clear to you. Okay, these are all things that you can easily miss or slip in the first time you're doing this. So please do ask if there's any questions. Okay. But notice, sir, please repeat this. All right. Okay, so is this much clear? I am looking for the components of A in the new basis vector. So just like my components of A in the old basis vectors are things like 1A1, 1A2, the components of A in the new basis vector, in fact, let me write it out completely. So A in the new basis is given by the 1, 1 component, or the E1, E1 component, and the E1, E2 component, and the E2, E1 component, and the E2, E2 component. Okay. My basis vectors have gone from 1, 2 to E1, E2. I hope this is okay. So to understand what the components of the matrix A are, I need to figure out all these matrix elements. Okay, all these different things are called matrix elements because they are the elements of a matrix. So we are first trying to work out the first element, E1, A, E1. Okay, so remember that there is 3 different objects in this element. The first object is bra E1. The second object is some abstract A. And the third object is the ket E1. Okay. Now I know the elements of A in the 1, 2 basis, which is this. Okay. So using this, I want to figure out what the elements of the matrix in the new basis is. So the way I will do this, why aren't we directly using bra and ket of E1, E2? Is it necessary to use basis 1 and 2? So the point is that if you change the basis, the components of a matrix change. Okay, so remember that when all your school life, your teacher gave you some matrix and they asked you diagonalize this matrix and write down the eigenvectors, right? All right, so you diagonalize the matrix and wrote down the eigenvectors. Now, there was something curious about this whole prescription. So suppose if you write down the matrix, let us say that your teacher gives you a matrix, let us say some 2 by 2 matrix, and he asks you to diagonalize them. So I hope that you have all taken a linear algebra course and you know that how to diagonalize a matrix. Okay, the way you diagonalize a matrix is write down the eigenvectors in a matrix form. If not, we will revise this. And then work out the combination. If the matrix of the eigenvectors is some matrix S, then work out the combination S inverse AS. And S inverse AS becomes a diagonal matrix. Anyway, if that doesn't make sense, don't worry about it. The point I'm trying to make is that the components of a matrix depend on which set of basis vectors you take to describe the space you are in. If I describe my two-dimensional linear vector space using this 1, 0, 0, 1 basis vectors, then my A looks like this 2, 3, 4, 7. If I change my basis vectors to something else, then the point is my matrix also changes. So I'm trying to work out what is the change in my matrix. How does my new matrix look like in the basis vector E1? That is the question we are trying to answer. This method of sandwiching an operator between ket and bra basis to get the operator in terms of the new basis vectors applicable only for a set of orthogonal basis vectors, or does it apply to any set of linearly independent basis vectors? So usually when we write down basis vectors, we construct a set of orthonormal basis vectors. Of course, you can also write down any other set of linearly independent vectors that are not orthonormal, but then you cannot write down projection of this, and it's very difficult for you to understand this basis in any regularized fashion. So at least in physics, whenever I say basis vectors, I mean a set of linearly independent vectors that are properly orthonormal. You have missed a negative sign before bra 2 in bra 2. What did I miss? So sorry, just a second. Thank you. I think it is this. I hope that is what you're talking about selling. Thank you. All right. So this is my question. I want to figure out the components of a matrix. So Manik, I think I answered your question. So if that is okay, then fine. If not, ask any follow-up questions you might have. So I want to write down the components of this matrix in the new basis vector. So I will simply look at, so participants, okay. Look at this particular combination, and I will simply substitute what the corresponding bra vectors and row vectors are. So this is equal to, there is a 1 over root 2 for E1 coming from the left and 1 over root 2 coming from the right. So I'll club both of these things and write 1/2. And then I will write this as 1 plus 2 A1 plus 2. Okay. So again, this is nothing but the previous step. I'm putting the bra vector E1 in terms of the original basis bra vectors 1 and 2. And I'm putting the ket vector E1 in terms of the original ket vectors 1 and 2. So now I have to multiply, right? This is nothing like multiplying. This is x1 plus x2, a times x1 prime plus x2 prime. So there is 4 terms, right? x1a x1 prime, x1a x2 prime, x2a x1 prime, x2a x2 prime, right? So that is what I will do. So I'll multiply this and get the 4 terms. The 4 terms are, in this case, remember that the elements of a matrix are numbers, so I should get numbers out. The first element is 1, A1. This times this times this. Okay. The second element is this times this times this. So this is 1A2. Okay. The third element is this times this times this. So plus 2A1. And the fourth element is this times this times this, which is 2A2. So thus I can write the matrix elements of A in the new basis in terms of the matrix elements of A in the old basis, as long as I know what the transformation rule between the two basis vectors are. So this is the transformation rule. Equations A and B are the transformation rule in this particular case. And this is how you work this out. So what is the 1, 1 element or E1 element? This is the 1, 1 element, 1, 2 element, 2, 1 element, and 2, 2 elements added. So this is nothing but 2 plus 3 plus 4 plus 7. So this is what? 2 plus 3 plus 4 plus 7. What is this? This is 5, 9, 16. So this is 8. Yeah. So let me work out one more and then I will stop, because I hope the procedure is clear. So let us work out the E1, E2 element. So E1, A, E2. What is this? Again, there is 2 1 over root 2's from both of these bras and kits. So I will club this and write this 1/2 times equals 1/2 times E1 bra is again 1 plus 2 A. Ket E2 is 1 minus 2. So this is again, there is 4 elements. These are 1A1 minus 1A2 plus 2A1 minus 2A2. Okay. This is nothing but 1/2 times, I should look at my matrix again. So I've written it over here. The 1, 1 element in the original basis is 2. The 1, 2 element is 3. So this is 2 minus 3. The 2, 1 element is 4. So this is plus 4. And the 2, 2 element is 7. This is minus 7. 2 minus 3 is minus 1. 4 minus 1 is 3. 3 minus 7 is minus 4. So this is minus 2. Okay. So in the new basis, my A takes the form. The E1 element is 8. The E1 E2 element is minus 2. And I leave it for you guys to work out what the E2 E1 element is and E2 E2 element is. Okay. So I expect you to complete this exercise. So complete this exercise. Okay. So it will give you some practice in dealing with bra and ket vectors. All right. So using this knowledge, you can answer the last problem, part B of the tutorial that was given, tutorial number 1, where I again give you the exact same thing. I gave you a 3x3 matrix, not a 2x2 matrix, and I asked you to work out what the matrix in the new basis vector is. Okay, so you can use whatever we have done here to complete that part of the problem in the first tutorial. Are there any questions or any comments? Questions, comments? Okay. So if that is okay, I will begin the theory of operators in quantum mechanics. And I will begin this by taking a very simple example. Okay. Operators in quantum mechanics. Okay. So the simple example that I will choose is something that you have already seen. So we have now dealt with objects using the Dirac bracket notation. We have dealt with objects of the form this, which we call ket vectors, and this, which we call bra vectors, and this is a scalar product, which is a complex number in general. And then we have dealt with something like alpha, a, beta, which are the components of an operator or matrix elements. These are the four kinds of objects that we have seen. Okay, ket, bra, complex number, and matrix element. Now I'm going to write down something that looks a little crazy. So before that, there is a question. A and the set of basis vectors are from different LVS. Then how does this process work, which is getting components of A from basis vectors? No, Sachin. So this is a good question and a common misconception. We are in the same linear vector space. Okay, it is a two-dimensional linear vector space. To describe a two-dimensional linear vector space, I need two basis vectors. Whether I choose the basis vectors to be 1, 0, 0, 1 or 1, 1 and 1 minus 1 is completely up to me. Okay. So to understand this further, think of rotations. Okay. Now, suppose if you are living in a very cool, very simple XY basis. Okay. All right. Now, you can write down any vector in this basis. So I'll write a vector of this form. Okay. I'll call this A vector. Now, this vector has components. So this is the X component of A, which is AX, and this length is the Y component of A. So you write this A as AXI plus AYJ. Okay. So these are the components of this vector. All right. But somebody comes along and says that, no, I don't really like this X and Y. So let me rotate this and goes to a new X and a new Y. Okay, that is at an angle theta with respect to this. So this is your new X axis. This was your old X and this is your new Y axis. Okay. Now what will be the, so now you cannot claim or you cannot tell that person that what you're doing is completely wrong. Now you're changing the linear vector space. He is not doing anything to the vector space. He is just viewing it from a slightly different angle. That is all, right? So he's just rotating the basis vectors. And when he rotates the basis vectors, he is also rotating the basis vectors. He is rotating everything, right? Now this vector A, that is just there still. It is the exact same vector that was there. I have not done anything to this vector A, right? The vector is a vector. But now if I want to describe this vector using the X prime and the Y prime axis, you notice that its components are completely different. Right now, with respect to the X prime axis, this is if you should draw a perpendicular to the X prime axis, and then you should draw a perpendicular to the Y prime axis, and then you should figure out what the X component and Y component of the vector are in the new X prime Y prime axis. Right now, there is nothing in physics that tells you that you should only do physics in the original XY axis. In fact, the whole premise of physics is that you can do physics either in the XY axis or the X prime Y prime axis, as long as you know how XY and X prime Y prime are related. And you know how XY and X prime Y prime are related, right? This is basically cosine theta minus sine theta cosine theta times X comma Y. Similarly, the X component of X prime component of A would be cosine theta times the X component of A in the original one minus sine theta times the Y component of A in the original. But we are not doing anything to the linear vector space. It is still a two-dimensional linear vector space. We have simply changed the axis. Okay, we are not going out of the two-dimensional linear vector space. Just by rotating the axis, I'm not converting this two-dimensional space into a three-dimensional space, for example. I still need only two vectors. One basis vector along the x prime axis and one basis vector along the y prime axis. Okay, so think of this basis vectors and change of basis vectors in exactly the same form. Rotation is possibly one particular example. Okay, I'm not doing anything to the linear vector space as such. I just want to visualize two different LVS at the same time. I appreciate the enthusiasm, but in general, this is a bad idea. Trying to visualize linear vector spaces is difficult in quantum mechanics because, as you will quickly see, we will not be dealing with very simple linear vector spaces in this particular fashion. We are dealing with what are called Hilbert spaces, which are infinite dimensional linear vector spaces. So no matter how hard you try, you cannot visualize even one, leave alone two. Okay, so visualizing a linear vector space can work if you're dealing with very simple linear vector spaces, and it is a good exercise to visualize very simple linear vector spaces, two-dimensional orthogonal rectangular coordinate axis you can visualize. But even three dimensions, at least for me, is a little difficult. And when you go beyond three, it is impossible because our minds are not capable of visualizing a four-dimensional object because we are fundamentally three-dimensional beings.
Sir,
So visualizing is a little difficult task, but trying to understand this mathematically and algebraically is, you would find is a little more useful in the long run. But that is just my opinion. I will not stop you from doing whatever you want. Any other questions? Okay, so I will erase this part. And then I will simply introduce this. I'm going to introduce a new kind of object, okay, using the Dirac, Bra, and Ket. And I'm going to call this P alpha. Oh, again, my sharing is not working. So let me stop sharing and start sharing again. Sorry about that. Okay. Now, I'm guessing there's some question. Sir, how can one form A in linear combination of 1 and 2 bases? How can one form A in linear combination of 1 and 2 bases? I don't understand. See, again, take the rotation example. So you had a vector in XY axis, right? Now the vector was just remaining. Vector is some abstract object. Now in this case, you can visualize the vector as a directed line segment in space, just like your teacher told you in high school. So the vector is just the vector is the vector. The vector doesn't do anything, right? Now, if I change the coordinate axis to x prime, y prime, the components of the vector change. Just like that, matrix, you can visualize the matrix as some kind of an abstract object, mathematical object. The components, of course, you cannot visualize the matrix as a directed line segment, just like you can visualize a vector, but think of A as some kind of an abstract object. The components of this object depend upon the choice of the basis vectors. So if I choose my basis vectors to be 1 and 2, then my matrix looks like this, 2, 3, 4, 7. But if I change my basis vectors, if I shift my basis vectors to something else like this, then my my matrix is going to look completely different. Just like a vector looks different if you change the basis vector, the matrix also looks different when you change the basis vector. It looks like 8 minus 2 something something. Okay, that is all I'm saying. A is not a linear combination of 1 and 2 bases in a form. Okay, the way you project out the components of the matrix is a little more complicated. You sandwich the matrix between the corresponding Bra and the Ket vectors. Okay, so let me write down a new kind of object. Okay, I'll write down an object. Remember that a Bra times a Ket is a number, but I will write down a Ket times a Bra like this. This obviously is not a number. Okay, Now, as of now, if you don't know what an outer product of two matrices is, this might be a very strange object for you. Okay. But even though this looks like a very strange object, and I've also put a hat on top of this P alpha, even though this looks like a very strange object, I can try and understand how this P alpha acts on some other vector. How does it act? So suppose if I take P alpha and multiply it or act it on some vector B, beta. What is this? P alpha is alpha, alpha, beta, right? Now, what is the inner product alpha, beta? It is the component of vector beta along the direction of vector alpha, right? That is the whole point of the overlap of two vectors. If I take the bra alpha and multiply it with the vector beta, it gives me the amount of beta that is aligned along the alpha axis. Okay. So even though this P alpha, which is a ket times a bra, looks like a very strange object, the action of this P alpha on any other vector has a very simple interpretation. It projects out the amount of alpha, the amount of any vector along the direction alpha. So for this reason, this P alpha is called the projection. I will write it more clearly because this is important. Projection operator. So this is your first introduction to operators. Operators by themselves do not have any meaning. If I gave you P alpha, 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 and told you, tell me everything about P alpha, you would look upon me like I'm saying something very weird. And I am saying something weird. But if I tell you what is P alpha acting on beta, then that is a well-posed question because it has a very specific answer. It gives me the amount of beta along the direction of the vector alpha. So operators in quantum mechanics or in operators in general have to be understood via their actions on the vectors. Okay. So operators act on vectors. Now notice that P alpha acting on beta is the amount of beta along the direction of alpha, but it is just not a number times the vector alpha, right? So the action of an operator on a vector gives you a new vector in general. So operators acts on vectors to give you new vectors that live in the same linear vector space. Otherwise, the operator is ill-defined. The operator should not take you outside of the linear vector space. Okay? So an example would be a rotation operator that we just discussed. So I have a rotation operator in 2 dimensions. So I can think of this as a matrix that takes a vector xy, okay, cosine theta minus sine cosine, okay. I can think of this as some operator r acting on some vector v, and this gives me a new vector v prime, okay. R acting on V give me a new vector V prime. So this rotation, I can think of it as a rotation operator R acting on a vector V in a 2-dimensional linear vector space, giving me a new vector V prime, a rotated vector in the same linear vector space. So this is how operators act. In general, operators, let me use a symbol K, operator act on vectors alpha and give me another vector alpha prime that lives in the same linear vector space. This is the action of operators. Okay. Now, since we have talked about projection operators, I will end this discussion by talking something very nice about projection operators and something nice about the general construction of basis vectors. So before that, let us understand something fundamental. So how do I know how the operator acts on a vector alpha? So I know that the vector alpha can always be written as a linear combination of the basis vectors, right? So K acting on alpha can be understood as AI K acting on each of the basis vectors. And I will talk more about this property. I was a little quick here. It is not at all obvious that K acting on alpha can be written in this particular fashion as it is on the right hand side. These are what are called linear operators. But the point here is that if I know how K acts on the basis vectors, EI, I know how K acts on every vector alpha. Okay, so it is very important to understand how any operator acts on the basis kits. That is point number one. Point number two is again something about the projection operators. So instead of projecting around about some random vector, let us project along one of the basis vectors. So let us take the basis vectors to be some EI. Okay, I don't care about the number of dimensions. I could be 2 or 3 or 1056. It doesn't matter. Now instead of, so you guys know by this point that PI, which is EI, is a projection operator along the ith direction. Suppose if I take PI and multiply it or act it on any vector alpha, it gives me the amount of alpha that is lying along the ith direction. But suppose if I construct the sum over all the basis vectors of this operator, obviously this is also an operator. Okay, so let me call this P. Okay, let me not call this P. This will turn out to be something different. This is also an operator. It is a linear combination of projection of along all the different axes. Now let me take this and act it on some vector alpha. Okay. Now let me do this very carefully. This is equal to sum over I, EI. Now in this set of basis vectors EI, I can also write my alpha as a linear combination of the basis vectors. Okay, I'll write alpha as sum over K, AK, EK. So now there is two sums, I and K, EI. Now the multiplication of the bra and the kit, and AK is just a number, so I can pull it out. This is EI, EK. Okay, I hope this manipulation is clear. If not, please ask. But if these are a set of orthonormal basis vectors, this is nothing but delta IK. So this sum is only non-true for I equal to K. So this is a sum over two different indices, one set of I and one set of K, but this delta function forces you to choose I equal to K. So this is collapsing two different sums into one sum over only one index. We can call this either I or K, it doesn't matter. Let me call this K. This is nothing but, since this is delta IK, this is AK, EK. Okay, but what is AK, EK? AK, EK is nothing but alpha that we started with. Okay, so this is alpha. So this sum of projection along all the different axes on alpha gives me alpha back. If I am to think of alpha as a column vector, then this guy is a matrix. But what kind of a matrix? It is a matrix that multiplies any column vector to give me the same column vector back. So this guy has to be a unit matrix. Okay, so this is called a unit operator. So suppose if I take the projection along every single axis in a linear vector space and I sum over all the projections, then the sum over all the projections is unity. Is the unit operator, which I will denote by this particular symbol. And this is a very important property of basis vectors. If this is true, only if this relation is true, if this is true, then the set of basis vectors EI is said to be complete. And they are said to span the linear vector space. Okay, this is a very important property of basis vectors. You take the projection of the basis vector along any direction and then add all the projections along all the directions. And if the sum of this is a unit operator, then this is a proper indication that you are dealing with a proper set of basis vectors that are complete. Complete meaning this relation that alpha, any vector alpha can be written as a linear combination of these basis vectors makes sense. Okay, so this is a proof of concept in some sense. If alpha can be written as a linear combination of all the basis vectors, then whatever I've written in the boxed equation has to be true. Okay, so usually whatever is written in my boxed equation is taken as the definition of a complete good set of basis vectors. If this relation is true, then we are dealing with a complete set of basis vectors that span the linear vector space. Okay. So again, this is not a number one, this is operator one. Okay. So Manik, first of all, the fact that this is not defined is not true. For example, the multiplication of a row vector times a column vector is a number. But the multiplication of a column vector times a row vector is not a number, it's actually a matrix. It is called the outer product of two vectors. Okay. So this is not any kind of matrix. For example, if I am dealing with a complete set of basis vectors and if I add over all the projections, my claim is that this is a unit matrix. Okay. So the fact that it is not defined is not true. It is defined. It is called the outer product and it is in general represented by a matrix. So I will